Well, I'm VM, it's much easier to pronounce. I'm coming from the University of Belgrade, and before that I was on Purdue University, where I worked on DARPA first gallium arsenide microprocessor and multi-microprocessor. Now, basically I'm back again in the 200 megahertz arena, because the Maxeler machine is using Xilinx hardware, which runs on 200 megahertz. Well, so formally I'm from the University of Belgrade, but essentially today I'm speaking as a member of the Senior Advisory Board of Maxeler. And all presentations so far were covering a paradigm called ControlFlow supercomputing. Well, this talk is talking about a completely different paradigm, DataFlow supercomputing. Now, all computers on the top 500 list belong to the ControlFlow supercomputing arena. Maxeler is covering the DataFlow supercomputing arena. Basically, what's happening here? If you compile down to the machine code, which is what ControlFlow supercomputers do, then you achieve certain speeds. If you are able to compile lower than that, then you can get better speedups, you can get better electricity bills each month, you can get a smaller size and a lower cost. Maxeler is 20% owned by JP Morgan, and JP Morgan declares for their applications, compared to what they had before Maxeler. With Maxeler, they were able to achieve speedups between 20 and 200 times for the same purchase cost. At the same time, their electricity bills became 20 times smaller, and the size is so small that you don't have to build a new building for your next generation supercomputer. You can put it in a corner of your existing lab. However, there is no free lunch. There is a price to pay here. And these machines are more difficult to program. Consequently, these machines are good for the so-called warm applications. Write once, run many. And examples of such applications you can find in geophysics, in banking, in life sciences, in data mining. For example, Schlumberger and some other oil companies are using the Maxeler machine to decide where to drill in the ocean for oil. JP Morgan is using Maxeler for banking. Some people at Stanford and other universities for life sciences. And Google is now knocking on the doors of Maxeler about data mining from social networks. Well, just to remind you about the differences between the ControlFlow approach and the DataFlow approach. And the next slide basically tells you how you map a one-dimensional source code into a two-dimensional data flow graph. Nothing new. What's new, however, is that the technology has now come to the point when the old data flow ideas can implement for the best of the supercomputing applications. Well, this figure basically tells why is a data flow approach like Maxeler able to provide speedups over the competition, which is multi-flow and many-flow. The first graph is for multi-flow machines, this is for many-flow machines, and this is for Maxeler. Actually, takes lots of time to explain the details of this graph. However, those of you who are subscribed to communications of the ACM, if you just wait 2 more months, a paper of ours is coming, which describes all this in details. The paper was authored by people at Maxeler, myself, Mike Flynn of Stanford, and Matteo Valero from Barcelona Supercomputing Center. So basically it tells that if the software includes enough parallelism to keep the cores busy, and if the only limiting factor is the number of cores, then these graphs here hold, and we get the speedups that I had mentioned. Now, let's move to the anecdotic kind of explanation of the same. You all know, this is well known. Some people compare multi-cores with using horses to plow or to carry a wagon. So this would be an example of a dual core. Well, how the horses know where to go? Well, for that to happen, you need a driver. And in order to explain that driver what you need, what you want, this guy must be equipped with caches. Now we see with NVIDIA they even have the ROD cache on the top of the L2 cache. You need predictors, you need all kinds of everything. In case of many cores, this is also well known. Instead of 2 horses, you can use 2,000 chickens. And here, however, you need more than one driver. You all know why. And if you remember one of the early morning keynotes, if you are using the remote CUDA, in addition to those subdrivers, you need also a dispatcher, correct? Well, the next question is, what would be the analogy that one can use with Maxeler's approach? So what's here? What do you think? Let's have a look. Well, basically this is like using 2 million ants to do the same job. The assumption is that each ant carries a backpack with some data in it. Well, so how we do the computation? What's the model here? Well, what you have to do first is to take your Maxeler machine, to view it as a field, as a huge gate array field, and then you have to place around the gates to correspond to your application. And then you load the backpacks of your ants with data. The more data, the more sophisticated the data are, the better an approach like Maxeler. Here, we are talking about big data. You know the term coined recently by President Obama. So, you remember, for multi-cores and many cores, in order to tell your wishes, you need to write code, and the hardware has to be equipped with all kinds of everything. What you need here, however, is only a plate full of marmalade. No caches, no predictors, no nothing. Why? Well, this is a gate array-based implementation. So what you need is a voltage difference between input and output. And that drives the electrons, and actually that drives the ants in our analogy. So what happens? You let the ants go through, and you get the results. So this is how the Maxeler DataFlow approach works. In general, if you remember the literature from 60s and 70s, there are 2 basic approaches to data flow computing. Coarse grain like HEP, and fine grain, and that's what Maxeler is. So why is Maxeler so much faster? As I have said, for some of its applications, JP Morgan is publicly announcing the speedups of 20 till 200 for the same initial investment compared to what they used before Maxeler? Well, you remember, if we compile down to the machine code level, there is so much that we can get. In case of DataFlow, we compile all the way down to the level of gates and wires, and that's where we execute. And it's intuitively more clear that the deeper the compilation reaches, the more benefits you can soak out. So why are the electricity bills so smaller? Well, multi-cores and many cores use the clock that is used by the microprocessing infrastructure they are built on the top of. Well, in this case, we use a much slower clock. If you remember the communications of the ACM paper from 2 months from now, graph, you will see over there everything works on a much slower clock. And actually the clock ratio here is about 20 to 1. Currently there is a big hype going on in Hungary. Why? CERN off-placed one of its supercomputer machines worth 10 million euros to Budapest for the whole Europe to have a free access. Well, a newspaper man figured out that the electricity bills for that machine will reach the same initial investment of 10 million euros in only 2 years. And now you have articles like, you know, poor Hungarian taxpayer paying for the rich Swiss, you know, to run supercomputing applications and things like that. Well, here, if one uses a Maxeler approach, the electricity bills are 20 times smaller, and this is not an issue. Now, why is the cubic foot so small? Well, multi-cores and many cores are implemented on the top of off-the-shelf microprocessors, where only a small portion is for data processing, and most of that is for process control. And DataFlow is implemented out of the FPGAs, where it is the opposite. So here it's like 5% over 95%, and here is the opposite, which is exactly 20 to 1, which is what I was mentioning. But you remember, there is no free lunch. The programming effort is more difficult. Well, this is what multi-cores do, and this is what many cores do. In the case of DataFlow, you have to make the field with processing gates, and that takes time. Basically, you start from the same program in C, which was written initially for the supercomputer application that you like to run. Then, wherever you see a loop that you like to port to the Maxeler accelerator, you substitute that loop in your C code with call Maxeler and get data back from Maxeler. And then you have to write 5 different Java programs. One for the kernels, which define the flow, one for the manager, which puts the flows together, then for the simulator, for the real hardware, and finally a script file, you know, to put all that together. The more code you have, the more sophisticated is the debugging effort, and compilation takes more time. Now the fun part. You know, many centers of excellence, before they decide to port in a new supercomputer, they have to build a new build. Horses need a big build. For chicken, it's easier, and for ants, they are happy with a hole in the ground. You remember I said you can keep it in a corner of your lab. Prices of Maxeler machines go all the way up to 100 million euros, and that machine is not bigger than this desk. Fortunately, they have a university support program for only about 10,000 euros. And many universities all over USA and Europe are now using this machine and having their grad students experiment. Now about the energy. It's expensive to feed horses. It's much easier to feed chicken. And for the ants, they're happy with cats. So the question is, who is faster? Everything boils down basically to who's faster. Well, if you have some small regular data, then obviously horses will be much faster. Well, if you have more complicated data, the line is much steeper now. Well, the horses cannot run that fast on a steep ground, while chicken would be faster than ants. However, the question now is who can climb a vertical wall. So let's see. Well, only the ants can climb such a wall. So with all this in mind, this is what the major concerns are now with Maxeler as far as how to enter the Exascale arena. And next. And as far as the details, I'm now passing the pumpkin to Oliver, who will tell you more about the details of what's going on.
Okay, thank you. So that's sort of a general overview of what the DataFlow computer would actually do. I'm going to show you a little bit more on the practical details of what one actually looks like and how you can put them together to build real systems and run real applications. The key part being that this DataFlow engine is a coprocessor. You've got thousands of tiny cores running repeated calculations. You've laid them out to run in a regular grid for your application, and you stream data through that, which means you have to have a lot of data you actually want to process. And in most HPC applications, you do. But you don't at every point in your program. When you're just booting up, you want to process a file name and then load something from disk and then ask the user whether they want to run, etc. So we still need ControlFlow systems. We need commodity, conventional processors to actually run our programs. And we're going to use the DataFlow engines as a coprocessor in the same way as we might a GPU or a DSP or any other kind of coprocessor system. But there are lots of different ways in which we can combine these systems together, some of which we've been hearing about in terms of other architectures, in terms of RCUDA and directly coupled GPUs within nodes from HP and that kind of thing already today. This is the way that Maxeler does it with our 3 data center hardware systems. So we have C series and X series targeted at HPC, and N series, which is really targeted at very low latency communication systems. And they have different characteristics which map differently for some different applications, so it's worth looking at. This is the C series architecture. This is a straightforward CPU-based system and some number of DataFlow compute engines connected over PCI Express. But we also have this additional interconnect here, which is worth noting. So as well as being connected to the CPU, each DFE is actually connected to its neighbors in an interconnect we call Maxeler, which is dedicated point-to-point, very low latency, very high bandwidth. And that's there precisely to handle some classes of HPC application where we're decomposing a problem across these multiple processing engines, and we need to be able to communicate between them directly very, very fast. A couple of examples of applications mapped to this kind of architecture. This is a JP Morgan application that was published in 2010. It's a credit derivatives valuation and risk calculation. So this is computing the value of what's called a complex tranched product. For the people who have not encountered these are the financial products that destroyed the world in 2008. This is taking a large set of derivatives and then stacking them up in a portfolio and selling off chunks of the portfolio. The computation to actually work out the value of that chunk of the portfolio is very, very complicated because it depends on the correlation between the different constituents of the portfolio and how likely they are to default and what recovery you're likely to get in the event that one of them defaults. And so this is a computation that's typically run in banks overnight. And so at the beginning of the next day, you will know what the risk position you had was at the end of the previous day. Of course, the stock markets or the derivatives markets open at 9 o'clock. or 8 o'clock, or whenever it is, depending on which market, and by 9:01 all those numbers are now out of date. You now wait a day until you're in a position to figure out again what your risk position is, and you hope you don't lose too much money in the meantime. Speeding this up is therefore quite valuable, and in fact what JP Morgan were able to do is to reduce the runtime from something like 8 hours down to a few minutes. And this can now be run in intraday. There's a really interesting number here as well, which is this is running on a C-series machine. The power consumption of that machine actually drops, even though it's running an order of magnitude faster. That's because the Intel x86 CPUs in there were actually able to throttle down. Of course, there's another way of looking at that, is that they're a complete waste in this system, and we really should have found something else to do with them, which is where the X-series hardware comes in. Different type of application. This is a seismic processing application with a publication again in 2010-2011 from ENI. This is a multi-dimensional search application, about as different as you could possibly imagine. You're trying to find the best parameter set for these 8 parameters that's going to identify a point in 3-dimensional space. You have to search in this 8-dimensional parameter space, and you have to search that for several tens of thousands of points in a single work item. The typical runtime for this kind of processing is of the order of 1 month on a 1,000-core cluster before acceleration. Again, accelerated on a C-series system. This is delivering speedups around 200 times. This was a small number of DFEs compared to a single CPU core. Again here, the CPU cores were more or less idle when this computation was actually running. You're looking at a parallel portion here that was in excess of 99.5% of the application. All of that was moved onto the DataFlow engine. The CPU was really just doing management. And we were looking at the results that we were seeing with some of these applications and wondering whether we could do something better to make better use of our CPUs, which were otherwise just sitting there burning admittedly idle power, but still power, doing very little for us. So we came up with this. This is the MPC X series architecture. The core concept here is to take the DataFlow engines and to make them shared resources on the cluster. So this is a 1U chassis. It has 8 DataFlow engines with a max ring interconnect between them, and it has dual InfiniBand uplinks to the network. There are no x86, there are no Xeon CPUs in here. It doesn't run programs. What it does is it provides DataFlow computing as a resource on the network. From my normal computer program running as a process or a thread on a conventional PC somewhere on that InfiniBand network, I make a function call, data and computation. Data gets squirted across, computation happens, and data returns. It's transparent. I use the same API as I would if I was running it locally. In fact, I may not even know whether the computation is running locally or remotely. From a user perspective, all I have is CPU processes communicating with DataFlow processes, and I can get the performance that I get from the DataFlow offload without needing to worry about load balancing my CPUs and DataFlow engines on a per node basis. There are a few major classes of application that this allows us to do some really clever things with. One of the classes is what we would call a coarse-grained stateful application. A lot of conventional HPC and big science applications fall into this category. Things like modeling fluid flow or wave propagation or that kind of thing. Another class, which is much more common in commercial HPC applications, things like financial applications, is what we call a fine-grained stateless. This is where we're actually going to execute a computation which is going to leave no state behind and is going to complete within a few milliseconds. We're going to have many, many millions of these computations to complete. And this is a type of application where latency becomes really critical. Even though we're dealing with a throughput application, if we had to issue memory allocations, memory copies, then a compute, then a memory copy back, all of these data bouncing backwards and forwards across the network would kill us if we're only going to run a millisecond worth of computation at the other end. So the X series is designed specifically to optimize this kind of calculation. All of this communication is managed in hardware without any software involvement. And finally, there's an extension of this, which is a fine-grained transactional application, but with a shared database. And I'll give you some examples of these. This is a wave modeling application. a similar example to, as mentioned to motivate RCUDA in terms of using multiple GPUs together, one of the reasons that this application is so interesting is that depending on your input parameters, the memory usage scales dramatically. You're looking at a memory usage that scales with the third power of frequency, a runtime that scales with the fourth power of frequency. So to actually statically allocate a certain number of DataFlow engines to a certain number of CPUs can be quite inefficient if you have a wide range of parameters you want to actually run in your application. What we have here is the performance numbers running on 1, 4, or 8 MAX2 DFE cards as for different frequencies. You probably just about see the numbers. What the highest end system is delivering the performance about 2,000 x86 cores in that system. Using the X series, we can scale that up or down pretty arbitrarily. Where there is a max ring interconnect present, this is an application that can be decomposed in one dimension, and all of the boundary communication between the different processors just happens over the max ring automatically. We don't need to burden the InfiniBand network with any of that communication. This is a completely different application, stateless. This is a Black-Scholes option pricer. It's part of a computation called value at risk, which is really working out what the tail risk that you face as a financial institution is based on the portfolio of contracts that you own. You have to analyze many millions of scenarios. Each scenario computation is very, very small. And so you want to be able to run this. You want to have a lot of CPUs which are all preparing scenarios, doing the pre-processing and post-processing, and every so often you come across this block of computation which in the original calculation would have been dominant, but now it's down to maybe only a millisecond worth of runtime. You want to send that to the DFE and get it back immediately. Finally, one other class of application, the shared data transactional applications, covers a whole wide range of very interesting commercial HPC applications, particularly in the areas of searching. Things like text searching against documents, calculating shortest distances to coordinates against databases, sequence alignment on genomes, all fit into this kind of paradigm, and all of which can be run very, very optimally on an X-series system where you have a single transaction to the remote engine and back again. So, in summary, DataFlow computing is really focusing on data movement and moving data through computation that's laid out statically on a chip, utilizing a massive parallelism at low clock frequency to achieve that. This is going to give us performance, power efficiency, smaller system size, and it helps optimize the data movement, which is the key challenges of exascale computing. But we still need a mix of DataFlow and ControlFlow with interconnect and storage and all of our other systems at a system level. So in terms of addressing the challenges of exascale, though, what might be next?
Well, what we believe is the next step is the tri-peak. What I have put, no, go back please. What I have put here is BSC plus Maxeler, because the idea about tri-peak was born during a lunch. Alex Ramirez, Edu Aguade, Xavi Martorell, and myself in Barcelona earlier this summer during the time when I was giving a master course for BSc on how to program the Maxeler stuff. Well, you all know, as you will hear from the presentation X+2 by Alex Ramirez, currently BSc is working on its X+2 generation supercomputer, and that one will be called, if I'm correct, Mont Blanc. Why Mont Blanc? First, because it is the tallest in Europe, and this is supposed to be the fastest machine in Europe. And number two, because Mont Blanc has two peaks, and these guys are combining multi-flow and multi-core and many-core. Well, what we believe, however, is that the best solution is in the tri-peak. There is a mountain in Pyrenees with tri-peaks. Actually, I have noticed in almost each and every country there is a mountain called tri-peak or something like that in the local language. So we believe the smallest of the three should belong to Maxeler. Why? Well, if you combine the best of the three words, then you can get some important advantages. And actually, we believe that a marriage between Mont Blanc and Maxeler can be a happy marriage. And you know, in each happy marriage, it's known who does what. What we are now working on is an intelligent scheduler, which is partially implemented for compile time and partially for runtime. At compile time, that guy can check what part of the code fits best for Mont Blanc and what part of the code fits best for Maxeler. And then at runtime, a runtime facility which is built into the Mont Blanc operating system can recheck if the compile time decision made by this guy was a correct one, and then if not, it can be corrected online. Well, now I have a bunch of slides that bring lots of analogies, but I leave that up to your imagination to tell me what are the analogies that can be used here. And we are now open for questions, if you have any.
Any questions?
One more reason to consider this opportunity. You, as I have said before, you know, Maxeler is now clocking its FPGAs of Xilinx with a 200 megahertz clock. There is a company called Tabula in the USA, which promises FPGA at a speed of 1.6 till 2 giga. Well, if that turns out to be a solid approach, then just overnight, by substituting the stuff in the sockets, more or less, this approach can run from speedups between 20 and 200. You remember the JP Morgan data, all the way up to speedups between 200 and 2000.